Problem 739 is a multi-stage compressor problem. And here we have air at 1 atmosphere and 35 degrees C is compressed in a staged reciprocating compressor. So this is a piston cylinder compressor with intercooling to a final pressure of 50 atmospheres. And so what the intercooling means is that there is a heat exchanger where the hot air coming out of the compressor stage is then cooled back down to a lower temperature before it goes into the next compressor stage. So for each stage, the inlet gas is 35 degrees C. The maximum allowable temperature for the outlet of each stage is 200 degrees C. Mechanical power is the same for all stages, and the isentropic efficiency is 65% for each stage. The volumetric flow rate of air is 0.5 cubic meters per second at the inlet to the first stage. So we want to know how many stages are required, what is the mechanical power requirement for each stage, what is the heat duty for each intercooler, and if we use water as a coolant for the intercoolers and it enters at 25 degrees C and leaves at 45 degrees C, what is the flow rate of the cooling water that we're going to have to use for each intercooler. And we are told that we can assume that air is an ideal gas with a heat capacity of 7/2 R or 3.5 R. So I've got some preliminary information here. Just to reiterate, we have a multi-stage compressor. Our working fluid is air. We assume that the compression is adiabatic, but there's interstage cooling. And so what that means is we are assuming that the compression is separate from the cooling. So the compression is adiabatic in the little piston cylinder part of the device, and then the air flows out as it's compressed. It flows out through the little heat exchanger, the interstage cooling, and that's where the heat is lost. So I've drawn it here as one single unit just for simplicity, but we are considering the compression and the heat exchange to be separate little units in our system. The efficiency of each stage is 65% with respect to isentropic operation, and again we're told, just reiterate, that in between each stage we go back down to 35 degrees C, which is 303. Sorry, that's a mistake. That should be 308. 308 Kelvin. All right. So I've got my entering information. I got my final information, 50 atmospheres or 5 times 5,000 kilopascals. That's pretty high in my flow rate. The first thing that I want to do before I get started, we're going to have to calculate the power based on the flow rate, based on the air flow rate. And so we've got a volumetric flow rate given to us, and so I want to convert that. We can convert that either to a molar flow rate or a mass flow rate. I'm going to leave it as a molar flow rate, and it's nice that we were told that this is an ideal gas. And so this is based on the inlet conditions. And so I'm going to calculate the moles flowing in at the inlet. And so that's P times V over RT. And so we plug those values in for P1, our inlet pressure, our volumetric flow rate, ideal gas constant, and our inlet temperature. And we get a value of about 19.8. That's a pretty high flow rate, but that's what we're given, so we'll go through it. All right, the next thing that we want to do for a multi-stage compressor is we want to get an idea of how many stages we're going to need. And if you remember our rules of thumb handbook for compressors, this is a reciprocating compressor, and our overall compression ratio for the entire thing is 50, which is really high. That's way too high for a single stage compressor. And so we're going to have multiple stages. So how many stages will we need? Well, your book doesn't have this equation, but our handbook does. the number of stages. We want our, for a reciprocating compressor, we want our pressure ratio for each stage to be somewhere between 1.2 and a maximum of 4 per stage. And so what I've done then is I've taken this equation and you set up a little series, and you can do this in MathCAD. You set up n as my counting variable, so n equals 1 comma 2 and then colon. So if I want to set up a series, n gets 1 comma 2, and then that sets my interval. And if I want to continue that interval, I just press colon, the colon key, and that gives me my ellipsis. And then my final value, I just enter, and so I did that as 5. So those are my values. I'll consider up to 5. I really shouldn't need more than that. And then I can have it calculate the ratio based on that, and so that's type ratio. And then I use the left bracket, gives me the index. Left bracket gives me an index that's different from a subscript, the left bracket, and then I can use n as my index. And so if I bring that over, I set that up, I just type n equals, and it will print out my little vector of my index for the number of stages that it's considering. And then the ratio per stage is given here. And so you can see, of course, if there's one stage, there's a ratio of 50, that's much too large. 2, that's not going to work. 3 stages, you see that our ratio here is about 3.7. That's pretty close to 4. That's a little too close for comfort, I think, because remember what we need to worry about. We need to worry about the temperature of the outlet gas from each stage. We don't want it getting over 200 degrees C. And so there's a risk if we are running right up at the limit, we may get an outlet gas temperature of over 200 degrees C, and we'd have to go back at another stage and redo all the calculations all together. And so what I decided is that 4 stages is probably going to be good enough. With 4, our pressure ratio, compression ratio for each stage is going to be about 2.7, 2.66. That's kind of right in the middle. It's not too high, but it's not too low either. You see, if we go to 5, we've only got a compression ratio of about 2.2. That's probably a little bit of overkill. If you're going to design a final compressor or size of compressor, you might want to look at, say, 4 and 5 and consider some other ancillary things like the upfront capital costs, installation costs, and the running and maintenance costs. But let's go with 4. And so I am going to set the number of stages at 4. So n equals 4, and our ratio, compression ratio for each stage is going to be about 2.66. All right, so now we can start actually solving the problem. We're going to look at the energy balance equations, and we're going to look at the first stage. We're going to calculate the work and heat that needs to be removed, and then we'll repeat that for the second, third, and fourth stages. So now that we've decided the number of stages, the rest of the problem is pretty much the same as a very simple one-stage compression problems that we have worked in the past. And so we were given an efficiency of 65%. And so we have to do the same kind of calculations we did before, where we will do an isentropic work calculation. We will then apply the efficiency to get the real work. Then remember, we have to calculate the temperature, so we'll calculate the real outlet temperature, make sure we're under 200, and then we'll calculate the heat that is required in that intercooler to lower the temperature back down to, and again I messed up here, it should be 308 degrees Kelvin. So like our other compressor problems with our energy balance, we assume that the changes in kinetic and potential energy are negligible. Remember, we're also assuming that air is an ideal gas. That makes things a lot easier for us in the calculation steps. And we're assuming that we have constant heat capacity, so that makes things easier too. So with these assumptions, our energy balance for this open system, and remember this is an open system, even though the reciprocating compressor is piston cylinder, this is an open system. We're treating this as an open system, and so our energy balance reduces to the work is equal to delta H. And if we want to include the mass or mole flow rate, we would multiply by that. Now, the energy balance for the cooling of the air is just Q is equal to Cp times delta T. And so whatever our outlet temperature is, remember we want our outlet temperature of our compressor will be pretty high. We want to cool that back down to 308. And so we will use the heat capacity of air, multiply that, and we'll get the cooling duty that is required. The one thing I'll note is we are not interested right now in any of the design of the heat exchanger that's being used. We just want the total amount of heat or the total heat rate that needs to be transferred. Details of a heat exchanger, that will be something that you would consider in your heat transfer class that you would be taking in usually your junior year. Now, I went ahead and gathered all the properties of air. We won't need very many of these for this problem because we simplified to an ideal gas, so we don't have to worry about this. I did put the molecular weight in case you wanted to convert to a mass flow rate instead of a mole flow rate. And so this is in your appendix in the back of your book. And then they said to use 7/2 R, but in the back of the book in the appendix at 298, the heat capacity of air is 3.509, so just a little bit bigger than what you were told in the problem statement. So now we've got our properties. Now we can start our isentropic calculation. And so remember, this is an ideal gas, and if an ideal gas goes through an isentropic process, it doesn't matter if it's an open system or a closed system, because everything in this equation, the delta S, which is equal to 0, these are all state functions. And so it's Cp log of T2 over T1 minus R log of P2 over P1. Since we have multiple stages, I'm going to rename our outlet as T1 out and denote it as isentropic over T1, which is the inlet, minus R times the log of P1 out over P1. And so my P1 out is going to be the ratio, remember about 2.66, times my inlet pressure. So my outlet pressure for this first stage of the compression should be 269.4 kilopascals. So for this isentropic calculation, we can now solve for T1 out. So T1 out, isentropic, we rearrange, solve for this variable, and we get 407 degrees Kelvin. And if you can do the math in your head, you're a little bit better than me. But when I punch those numbers into my calculator, I get that is a temperature of 134 degrees C. So we are fine, at least for this isentropic. So remember, this is isentropic, but do you think that the real temperature is going to be much higher than that? It'll be a little higher, but we need to check. All right, so we'll check the real temperature, but so far it looks okay. So now we've got the isentropic temperature. We can now calculate the delta H for the isentropic case, and that gives us the work. And so I've combined a couple steps. Delta H for an ideal gas process is Cp delta T, and so the work is equal to delta H. So work for the isentropic in stage 1 is equal to the mole flow rate of air times the heat capacity of air times our delta T for the isentropic case, and we get the total power is 57 kilowatts. Now we need to get the real work. So to get the real work, we need to use the efficiency that was given to us. We were told that the efficiency was 65%, and so since this is a case where our surroundings are doing work on the system, we divide our isentropic work by the efficiency, and we get the real work for the first stage. And so this is going to be larger, which makes sense, because if it's very efficient, isentropically efficient, we should need less work. When we include all the irreversibilities, we need more work. And so we get work of about 87.9 kilowatt. And one thing you should note is this is a pretty big power number. 87.9 kilowatts. If you look in our rules of thumb chapter for compressors, you'll note that it's usually at a lower, this is above the typical value that we'll use for reciprocating compressors. But anyway, this is what the problem asked us, and so we'll go ahead and solve it for reciprocating compressors. So this is a real work. Now, we calculated the isentropic outlet temperature. We need to find the real outlet temperature of this gas as it comes out of the cylinder. And so what we need to do is we need to back calculate. The way I think of it, we're going to back calculate the temperature, because the real work is equal to the delta H for the real process, and that is equal to Cp times delta T for the real process. And so I set these terms equal, and I solve for T1 out. I call this T1 out real to denote it from T1 out isentropic. So I rearrange this equation, I solve for T1 out for the real process, and I get a value of 460.5 degrees Kelvin. This is about 187 degrees C, which is lower than the 200 degrees C maximum that the problem statement specified. And so from this, we are now pretty confident that 4 stages should be fine. Again, if you really wanted to, we could go to 5 stages. We would require less work per stage. We would have a lower temperature per stage, but of course you would be paying more for a compressor that has 5 stages versus 4 stages, most likely. So now that we know the real outlet temperature of our air coming out of this little piston cylinder device, we can calculate the heat that needs to be removed. And so that's just Cp delta T. And so because it's a delta H calculation, Q is equal to delta H. And so for the first stage, the heat removed is 87.91 kilowatts. And if you're paying attention, you notice that that is the same as the work, right? That's the same as the work. It's just a and this should be, sorry, I made a mistake here. This should be, I switched the signs. This should be T.1 minus real. It should be negative sign. All right. Work is positive because it is coming into our system, and I should have written this down. Remember, I'm using T1. That is my 308. That is the outlet temperature of my gas. So the reason why, and so that's the reason why these are the opposite sign, but they're the same magnitude. The same magnitude is because, remember, our inlet temperature was 308 Kelvin. It's heated up to 460, and then it has to be brought down to 308 Kelvin. And so the work went into heating it up, and then we have to take that heat out, and it turns out that these are the same magnitude but different sign. All right, so now we've calculated the amount of heat that needs to be removed from the air. So now we can do the water calculation. And so we set up our water calculation problem. We're going to assume that the heat capacity of water is constant. We can look this up. The heat capacity of water is about 4184 joules per kilogram Kelvin. The temperature of the water coming into our intercooler is 298, 25 degrees C, and we're told that the temperature leaving our intercooler is 318 Kelvin or 45 degrees C. And so we set up an energy balance for our water on the water side. The heat lost by the gas equals the heat gained by the water. And so you'll do a lot more calculations like this when you do heat exchangers, but this is a simple heat exchanger calculation where we are assuming that there's no heat lost to the surroundings, that all the heat that is lost by the gas is gained by the water. And so we set that up, and we are asked to solve for the mass flow rate, and I'm going to have to, I forgot my negative sign here, because this is actually the heat lost by the water up here is a negative sign, or sorry, the heat lost by the air is a negative sign, but the heat is gained by the water, so we have to negate that to put it on the water from the water perspective, and we get a mass flow rate of 1.051. And I should also put, if you're keeping track, we should also put a negative sign in here as well. But the mass flow rate of the water is going to be 1.05 kilograms per second, or about 1 liter per second, if you want to convert that to a volumetric flow at a typical somewhere between 25 and 45 degrees C. And so now we've completed all the calculations that are needed for stage 1. And what's nice about this particular problem is that our calculations for the following stages are exactly the same. Nothing changes. The inlet temperature is the same, the outlet temperature is the same, the flow rates are the same, the water flow rates are the same. And so all we have to do as far as sizing the entire compressor is just multiply the work values for the first stage times the number of stages. And so we see we get the total power required is about 351 kilowatts. That is pretty large. That's a pretty large number. And we note that in our rules of thumb little chapter, they recommended that anything that's above 75 kilowatts should probably be done by a centrifugal compressor. So maybe this compressor isn't the best thing, but at least we were able to do the calculation right. And you also see this mass flow of water, mass flow rate, 4.2 kilograms a second, or about 4 liters a second. That's also a pretty high number when you think about it. That's a pretty decent pump has to be supplying that kind of a flow rate for this system. And I'm not sure if commercial reciprocating compressors this large are going to be that common. So another reason maybe for moving up to a centrifugal compressor. Another thing to realize about this is we also assume that there were no pressure losses in the intercoolers, and you'll usually see a little bit of a pressure loss. Our handbook says maybe up to about 5%, depending on how the system is designed. We are also assuming that there's no leaking of compressed air in this system, and so hopefully that will hopefully our system is designed nice. We're keeping the temperature low, so we shouldn't have too much leaks, and hopefully our storage tank and all the other post compression air treatments that we do are also not leaking. But just realize that this number that we calculate for the total power needed for a compressor, we might want to increase based on some of the other factors that you will encounter in real life. But this is a good way, this is a good start for handling multi-stage compressors where the overall ratio is very large. It's impossible to do in a single stage. all we have to do is the only new thing that was introduced is we have to look at this ratio equation and find, based on our guidelines, what is a good number of stages to get a good pressure ratio, taking into account the suggestions from the manufacturers out there, the rules of thumb, and also taking into account that we don't want to heat our gas up too hot in one stage, and so we'll have to heat it or compress it, heat it, and then subsequently cool it before we do the next stage of compression, so on until we reach our final pressure that we need.